Hello, chemistry students. This is Mr. Ruby. This is a presentation on kinetics. So please have out your notebook, write down the questions, your answers, and revise when needed. What is collision theory? What is an activated complex? What is activation energy? How can reactions be diagrammed? How can we speed up a reaction? What is a multi-step reaction, and how do we measure reaction rate? So 7 questions. And all of this term kinetics has to do with the speed or rate of a reaction. So kinetic as in kinetic energy. So here we go. We have what's called collision theory. And this isn't the idea that if we want particles to react with each other, they have to collide. And as they collide, so we have a molecule of A2, molecule of B2, just smash together. And as they smash together, they actually have to absorb some energy to break their old bonds, so the bonds that holds the A together and the B together. And then when they form the new molecules, these new bonds between an A and a B, they actually release some energy. And depending on how much is absorbed or released, that's going to determine if the reaction is endo or exothermic. So we have this term, the activated complex. And it's a temporary arrangement of reactants. And it's where the old bonds break and the new bonds are forming. And it needs a couple things for it to work correctly. So let's look at the correct one first. So we have this collision. We have carbon monoxide, so see carbon and oxygen. And we have nitrogen dioxide. They smash together. And when they hit just right, and so they need 2 things for them to hit together and collide to form this activated complex. They need to have the correct orientation. So in this case, we have to have a carbon lined up with an oxygen. And they have to have sufficient energy, so they have to smash together hard enough. And if that happens, there's this brief moment where all of these atoms are sort of smushed together in this one thing. And that's where the old bonds are going to be broken and the new bonds will be formed. And then they'll form their new bonds. And as they form their new bonds, they're actually going to release some of that energy that was taken in to break the old ones. So in this example, they don't have the right orientation. It's oxygen against oxygen, and they just bounce off of each other. Once again, wrong orientation. We have oxygen with nitrogen. They just sort of bounce off of each other and rebound. This is the correct orientation, the carbon with the oxygen. But no, if you look, this is just like a wimpy little smashy sign, whereas these are bigger. So this has less energy or insufficient energy, and they just bounce off of each other. So that energy represented by this collision and how big this smash is, we call that the activation energy. And it's the energy needed to form that activated complex, the energy needed to break the old bonds of our reactants. And the more energy needed, the slower the reaction. And so what this is showing us is 2 different ways for a reaction that could happen. We'll look at this in a second, but this is where you start. So this is the amount of energy, or H, enthalpy, of our reactants. We need to give them some energy to break the bonds that hold them together so we can form this activated complex, and then new bonds can be formed and we can produce our product. Well, if we imagine the energy needed as a hill, well, the bigger the hill, so the more energy needed to get this reaction to start, the longer that reaction is going to take. So if you have a really big hill you have to get over to get your reaction started, it's going to take a long time. It takes a lot of energy to get it started. Small hill, doesn't take as much energy, won't take as long to get it started. And so we can show this with this little 2-dimensional diagram. We can show our potential energy on the y-axis and what we call the reaction coordinate or reaction progress on the x. Now progress is just sort of a general description of moving forward. It's not typically a unit there, so we don't usually see an amount of time. It's just we're moving forward in time, but we don't have a unit on it. And so we can look at this and make sense of this. So we can ask, is this an exothermic or endothermic reaction? Well, we start with our reactants, They smash together with the correct orientation and energy. So how do we represent that energy? We have to go up this hill. So we always have to go up some kind of hill to start these reaction diagrams. The distance from where we start to the top of the hill is our activation energy. That's the energy we need to put in to break the old bonds. Now we have our activated complex. This can form new bonds. Then as those new bonds are formed, energy is released, and we produce our products at this end. So notice our products have less energy than our reactants. So our chemical system has lost energy, or energy has flowed from our system to our surroundings. So we say it is a negative delta H, and it's exothermic. You look at this example. Is this endo or exothermic? Well, we're going in the other direction now. Got our CO2 and our nitrogen monoxide. They smash together with sufficient energy and the correct orientation. Well, they have to smash together really hard. Look how much energy they have to put in. From this starting point for reactants, they have to put in all of this energy. It's a huge hill they have to climb up and over to produce this activated complex. So it's a lot harder to break the bonds in these two molecules. Once we've broken those bonds, they can form new bonds. And as they form those new bonds to produce these products, some energy is going to be released. But notice, not as much energy is released in this one. So our reactants actually absorb more energy than our products are going to release. So in that case, we're going to call this a positive delta H. Therefore, it is endothermic. Our reactants, here's our chemical system. Our system has more energy when it finishes than when it started. So there's some ways we could make these reactions go faster. And one thing we can do is increase surface area. Here we have a list of them. So here's the 4 things we can do. I'll go through them one at a time here. So if you smash up your reactant into smaller and smaller particles, that just means there's more opportunities for collisions. You increase the surface area. So if I leave this peppercorn like this, I only can react with the outside of it. If I smash it into little dust particles, I can react with every little dust particle, and there's more chances to get that sufficient energy and correct orientation for my reaction. I also can increase the temperature, and this is with a gas is where this would happen. So if I increase the temperature of a sample of gas, what's going to happen is this curve is going to look different, and this curve represents the average kinetic energy. It's a way of mapping out the average kinetic energy of all the particles in my sample. So temperature 1, which is less than temperature 2, it's the blue line, so it's the cold one. This is showing you the number of gas particles and their energy associated with each particle. And the way you interpret this blue line is showing you, if you calculated the area under the blue line, that would be all of the particles in that sample. And notice the most number of particles is at this energy, which is a lower energy. So you have lots of these T1 particles that are in sort of this, whatever energy this is, slightly lower energy. They have some that are over here in high energy, and most of them are over here in sort of medium to low energy. Well, if I heat it up, so sample 2 is a larger value than 1, it's a higher temperature, what happens with my average kinetic energy? It increases. So I see a curve like this. So what's confusing about this, people look at this and be like, oh, it's a lower energy, it's a lower temperature. No, it's just there's fewer number of particles at this moderate speed. There's more and more of these particles at the higher speeds or higher energies. So this red line shows a sample of matter that's at a much higher average temperature. As you can see, the mean is at a higher temp than the mean of this low temp. Now, the last thing with this diagram, this has got a lot going on, is this line here. So this dotted line is showing us the activation energy needed. So it's that big explosion we were looking at before when the particles collide together. So you have to collide with this energy to make the reaction happen. Well, if you have a hotter sample of matter, then you have more particles that are at or above that activation energy. and we could calculate it. We're not going to do this, but if you took the area underneath the line, that would give you a sense of how many particles in that red sample were able to react. And look at that. It's about twice as much as the particles that are in the blue sample. So the blue sample only has the particles underneath this blue line that can react, whereas the red has all of these. Got to make it past that activation energy for the reaction to happen. Now you also can increase the concentration of something to make the reaction happen faster. Most basic level, if you have the same amount of volume, but you increase the concentration, if you have more particles per whatever that unit volume is, you've got a better chance of having successful collisions. So here, there's only 4 particles, so we hope that they smash together, 4 green and 4 red, whereas if we have way more particles, there's just a better chance of having the reaction work well, of having successful collisions. And the last thing we're going to look at is this idea of a catalyst. And we're definitely going to want to be familiar with these types of diagrams. A catalyst lowers the activation energy. It makes that initial hill that the reactant has to get up and over smaller. So these reactants with no catalyst, they have to take in this much energy to break their old bonds, whereas with a catalyst, they only have to go up half as high, maybe even less, maybe just a teeny tiny hill to get the reaction going. Key thing to notice here with a catalyst is that our reactants still start at the same energy level, and the products still finish at the same energy level. It's just a different pathway in between. And that's because a catalyst doesn't actually become integrated into the products. So we start with the same chemicals, we finish with the same chemicals. A catalyst comes in and helps them out, and then actually sort of gets spit out at the end and is not integrated into the products. Now, we're not going to look at multi-step reactions. The last thing I want to point out is how we actually measure our reaction rates. We've been talking about maybe we can speed a reaction up. Well, to get the average reaction rate, we take the change in the concentration of our reactant divided by the change in time. And we take the negative or opposite of that because the reactant concentration is decreasing. So we correct for that with this little negative sign in front. So delta of reactant concentration divided by delta time. And this would be an example. We start off with reactant purple cube, and then over time, its concentration changes until we have almost none of it left. So that would be a negative change in its concentration. And then we just divide that by the change in time. So let's say this took 1, 2, 3 minutes. So there we go. Good stuff. This is the last stuff we'll work on for this unit. So I will see you in class tomorrow. Bye.